So today we'll continue our discussion on photodetectors. Right. So basically, we mentioned last time that basically a photodetector is made out of the same material combination that we use for making sources like LEDs or lasers, right? And the same kind of idea. So we have a PN junction, except now the device is operated in the reverse bias region, right? For light emission, we operate it in the forward bias region. So for photon detection, we just apply reverse bias to this PN junction. Okay, so let's say there is some light incident from here with some optical power P incident. Okay, so there could be some load resistance. So basically, photons are entering this semiconductor, and basically the carriers here. So the electrons can absorb the photons and go from the valence band to the conduction band, right? And so basically, if you look at as a function of the depth within into the device, if I look at the optical power, right, as a function of distance that into the device, basically, you know that because of absorption, the power decays exponentially, right? So this is some function e to the minus alpha z, right? Where alpha is the absorption coefficient of this detector, right? So this alpha is of course related to this quantum efficiency and the responsivity that we talked about last time, right? So if you have a higher absorption coefficient, of course that means that your quantum efficiency and your responsivity are higher, right? So let's say if the total width of the device is W. Okay, so basically because of this light absorption, carriers are generated here, right? So electrons get excited to the conduction band, so you have electrons flowing in the conduction band and correspondingly holes created in the valence band, and these charge carriers can now be flow into the external circuit, and then you could measure, for example, the photocurrent coming out, or like have a load resistance and measure the voltage across some load resistance. Right. So if you look at the band diagram within the device, so this dashed lines here, of course, indicate the sort of depletion region where there are no free carriers within the device because of diffusion of electrons into the p side and holes into the n side. Right. We have this depletion region. And this depletion region actually gets widened because of this reverse bias which is applied. Right? So under no bias, there is some depletion region width, and you know that. So, for example, when we had forward bias for the sources, the depletion region actually maybe shrinks a little bit. When you apply reverse bias, the depletion region actually widens. Okay, and so if you look at the band diagram. So you know that because of this depletion region here, right? Because of this charge transfer happening, you know that there is an electric field set up, right, in the depletion region. So there is some band bending in the depletion region. Right, so this is the conduction band, the valence band, right? Of course, we choose the material such that the band gap is less than the photon energy, right? So basically, what you're doing is, so photons are coming in, right? So they excite electrons from here, valence band to the conduction, right? Leaving behind a hole here, right? And now because of this electric field across the depletion region, which has been enhanced because of a reverse bias, right? So again, so with this reverse bias, we call, so basically EF is somewhere here. Okay, so this is EF on the P side, close to the valence band, and here EF, the Fermi level, is close to the conduction band on the N side. Right, so this is the voltage reverse bias which is applied. Right, so basically you can see that as I apply more reverse bias, this band bending gets more and more severe, right? So this slope becomes larger, which means there's a larger electric field set up in this depletion region. And you can see, so as soon as the charge carriers are created, so electrons will flow down this potential hill quickly. Okay. So they'll quickly get attracted to the N side and flow out this way, while the holes, let's say, which are created here will flow like that to the other side. Okay. So basically recall that the electric field setup points from the N side to the P side. Right. So the poles are accelerated in the direction of the electric field, while the electrons are accelerated in the opposite. Okay, so basically, yeah, and then once they reach the contact, they come out as photons. So you can see that basically within this depletion region, because of this large electric field, the carriers flow really fast. Okay, so this region is called drift region, or basically where the carriers move with what is known as the drift velocity. Okay. So they are basically seeing a very large electric field, so they are flowing with what is known as a drift velocity, which is very fast. Okay. Whereas outside the depletion region, so here and here, you can see that basically there's no electric field to push the carriers along. Okay, and so here they are just flowing by diffusion. Okay, where basically so you're sending carriers from here, and basically there are less carriers here, so they sort of diffuse over time randomly to the side. Okay, so you can imagine, of course, that the diffusion velocity will be much smaller than the drift velocity. Okay, so the carriers flow really fast in this region, but then they're moving very slowly. Okay, and one sort of important metric that we want for photodetectors is a fast response time, right? So imagine, like, for example, this optical power is turning on and off at some data rate. We want this current also to follow that, right? So basically, we should be able to turn on and off the current really fast, right? So that, of course, if the carriers respond really fast, so if they are moving very fast, then they will. You can imagine that the response times will be smaller, right? Whereas here, like, if they're moving very slowly, even if you turn off the optical power coming from here, the remaining carriers will take a lot of time to diffuse out. Okay, so for example, the device turn off and turn on time will be slow because of this diffusion. Okay, so you can see straight away that basically what we want is that the depletion region should be almost the entire width of the device, right? Because this extra region outside the depletion region is slowing down my device or slowing down the response time. Okay, so we'll see in a minute what modification we can do to this simple PN junction in order to achieve that. But before that, just let's relate this. Right, so how much power is getting absorbed here? This is the incident power minus the power which remains at the other end of the device. So this is the power absorbed, the optical power absorbed within the device, right? So this is right because this is exponential dependence is just, you can see, straightforward like that. Right, and so this quantum efficiency that we defined, right? So that was the number of electron hole pairs created per second, right? Which is basically the number of photons absorbed per second, right? Because every photon which is absorbed is creating me an electron hole pair, right? So the number of carriers which are generated, that's just proportional to P absorbed, right? And divided by, in the quantum efficiency, we had the number of photons incident on the device. That's just P incident, right? So you can see that's just this. Okay. So the quantum efficiency of the device, right, which is basically the fraction of photons incident on the detector that generate electron hole pairs, right? So it depends on the absorption coefficient like that, alpha, and also the width of the device curve. Right, so you can see that if alpha W is much greater than 1, then this factor will be really small and your quantum efficiency will approach 100%. Right, so all the photons are absorbed and generating carriers, which is the best case scenario. Okay. So this alpha is of course a material constant, right? Once you choose some in-gas material, so this absorption coefficient depends on the material composition, right? So basically what you are free to choose is this W. So basically you want W to be much greater than 1 over alpha. Okay. But we can't make alpha with this W too big also, okay, by this argument that we just had, right? So if I keep increasing the width of the device, the depletion region width is sort of decided by the doping concentration, etc. Right? So that is sort of fixed, and also by this reverse bias voltage. So now if I keep increasing the width of my device to increase my quantum efficiency, you can see that the region over the device for which the carriers have to diffuse will keep increasing, slowing down the response time. Okay, so typically this W sort of an optimum value is kept like 3 times 1 over alpha or something, so that the response time is also not too slow. Okay, and there is also one other thing that can sort of reduce your effective quantum efficiency is basically, so again here, so imagine like there's an optical fiber here, right? And so the light comes out briefly into free space and then goes into a detector. So here you have a refractive index of 1, where here you have a refractive index again of like 3.4 or something. So there's a huge mismatch here, so you can get a huge reflection at the input facet. Okay, so you might just lose a lot of light here just due to reflection at the input facet itself. Okay, so to mitigate that, sometimes like you have you coat the photodetector here with some coating, like an anti-reflection coating. Depending on the wavelengths you want to operate the device at, so you make an anti-reflection coating at those wavelengths, and that you sort of eliminate this reflection. Okay, so this alpha, as you mentioned, is a material constant, right? So let's look at what this alpha looks like. So it's also a function of wavelength, right? Because again, you can imagine for a particular material, you have some band gap. So as I change the wavelength or the frequency, the absorption coefficient will change, because like again, the density of states we saw is a function of energy, right? And of course, if the energy of the photon goes below the band gap, then the alpha would just fall to 0, right? So as a function of wavelength, if you look at this absorption coefficient in per centimeter, for example, Okay, so again our telecom range is sort of somewhere here. What the y-axis? Okay, so the y-axis in log scale. So you know that silicon is a popular photodetector material. So for visible wavelengths, for example, we use silicon all the time. So if you look at silicon, it has a very high absorption coefficient at visible wavelengths, okay, but it falls down steeply because you know the band gap is 1.1 electron volt, which corresponds to about like a micron or so of wavelength. And not only that, like if the band gap is indirect, if you look at the direct band gap, the wavelength corresponding to that is about 800 nanometer or so. Okay, so typically we use silicon for visible wavelengths below 800 nanometer. So there are very good. So for example, on your cell phones, or if you even buy any commercial camera, the sensors, the CCD or CMOS sensors used typically are made out of silicon, right? Because detecting visible light. So if you look at these 3-5 materials that are important for our telecom applications, so if you look at gallium arsenide, it looks like that. Okay, again, still sort of restricted to visible near infrared wavelengths. One popular detector material for infrared wavelengths is germanium. So one row below silicon in the periodic table, right? So there you can go up to like 1.6 micron roughly. So germanium, you know, has like a band gap of 0.8 electron volts. So you can go to longer wavelengths. But germanium again has some issues regarding noise, etc. Also, the band gap seems being sort of indirect. So then we go to basically the in-gas P materials. Okay. So this is 70% indium, 30% gallium. (64% arsenic and 36% phosphorus. Okay, so you can see that that works well, for example, for 1.3 micron wavelength. If you want to detect across the telecom band the wavelengths of interest, so typically 1.3 to 1.6, 1.65 micron, then basically we go for just these in-gas photodetectors. So indium 53%, gallium 47%, and arsenic 100%, low phosphorus. Okay, so that enables me to detect in this telecom band of interest. Okay, so equivalently on sort of if I can plot 1 over alpha, which is known as the penetration depth. Okay. So basically, we want the width of the device to be, let's say, so here 3 times the penetration depth, right? So if I have a smaller penetration, so a higher alpha means smaller 1 over alpha, which means the power is absorbed very quickly, right? So I can make a thinner device, which is also helpful, for example, in terms of response time, right? So if you plot 1 over alpha or penetration depth on this side, so in micron, Okay, so basically here you can see we're talking about penetration depths of around a micron. Okay, or maybe a couple microns, 3 microns. Okay, so typically, so again, if you look at these in-gas photodetectors, the width of the device is about few microns, maybe up to 10 microns. Okay, and so for example, with a device roughly of 10 micron thickness, I can achieve this condition and a quantum efficiency of almost 100%. Okay, so I can make the detector very thin but also very efficient. Equivalently, if I plot this responsivity in amp per watt, right? Basically, the photocurrent generated divided by the incident optical power, again as a function of wavelength. So okay, so again recall that the responsivity depended on the quantum efficiency, was directly proportional to the quantum efficiency, and then wavelength. Right? So that was the uh, relation between quantum efficiency and responsivity. So you can see the responsivity for a given quantum efficiency scales with wavelength up to, of course, the band gap wavelength. Right? So basically, for a given quantum efficiency, it will be a straight line with respect to wavelength, right? Corresponding to a given slope. So, for example, okay, so these are the lines corresponding to different quantum efficiencies. So, for example, this is 90%, this is 70%, this is 50%, and 30%. So, again, if you look at different material systems here, so silicon lies here, that's silicon, okay. So, you can see that around the visible range of wavelengths where we can use silicon, we get responsivity about 0.6 amp per watt, corresponding to about 90% quantum efficiency. Germanium detectors typically lie somewhere there. Okay, so their quantum efficiency is quite poor. You can see 0.5 roughly. Right, again, responsivity you get about 0.5 amp per watt. Now, if you look at in-gas, so that goes something like this. So again, our wavelength of interest is this, right? So here basically these in-gas photodetectors have about 90% quantum efficiency and a responsivity of about 1 amp per watt. Okay, so these are real practical numbers, including like this initial reflection loss, maybe some internal losses of the carriers or photons to defects or something. Okay, so typical real devices that you can get in the market have these numbers of 90% quantum efficiency, about 1 amp per watt responsivity. Okay, so 1 amp per watt means, so let's say if you have 1 milliwatt optical power incident, that gives me a photocurrent of 1 milliamp, right? So that's gives you some scale. And typically, we study about noise mechanisms in these photodetectors in some detail. But one thing that happens is that because you have carriers here already because of this doping, right? There is what is known as dark current. Okay, so even if I block the input to the device here, there is no light incident on my device. Even then, there is a very small electric current flowing just because there are some carriers here and some thermally generated and excited carriers which have some kinetic energy, right? So that dark current typically for good photodetectors typically is limited to 10 nanoamperes or below. So you can see, so if our detected power is even in the microwatts, tens of microwatts or higher range, this dark current is negligible. But it might matter, for example, if you're doing on-off keying, right? For bit 0, let's say you're not sending any power, right? So ideally, your photocurrent should also be 0, but it will be non-zero. There will also be other sources of noise you can see, but this can, especially if the level 1 has been attenuated to a very small level, then it can give you some bit errors. Okay, so that's about sort of the efficiency of the detector is concerned, right? So now let's talk about this response time in more quantitative manner. Right, so imagine now, let's say, I have a bit stream coming in to my photodetector, right? So I have, of course, like in a real optical link because of dispersion losses and some other effects that we discussed, the received pulse here won't be like exactly square, but let's assume that we give some square pulse in optical power. Okay, versus time, so this is the bit duration here. So if you look at the photocurrent, or let's say the voltage across this load resistance, right? So it won't, of course, have an immediate jump. There will be some rise time, right? And also when you turn off the optical power, there will be some fall time. Okay, so this is the voltage or the current. Okay, so if you look at this response here, this is again like a typical exponential rise. So this is V of t is some V naught 1 minus e to the minus t over tau, where tau is the time constant. Okay, so just for like any RC circuit, if you have, right, if you apply a voltage step, then basically you know that because of the time constant RC of the circuit, there is a time constant for charging of the capacitor, for example, right? So similar thing happens here. So you can think of this photodetector as an equivalent RC circuit. Basically, you have a load resistance here already, and you know that there is a capacitance associated with this reverse bias p-n junction, right? So because it looks like almost a parallel plate capacitor with positive and negative charges, right, on two sides of a dielectric with the dielectric in between, right? So there's a capacitance associated with the device and also a resistance. So there is a RC time constant, right? One metric that is typically defined for these photodetectors is the rise time. So the time taken to go from 10% of the maximum voltage to 90%. Okay, so this time that it takes to go from 10 to 90%, that is the rise time, which is related to this tau. I mean, you can just put 10% and 90% in this expression. So this rise time comes out to be log 9 to the natural base times tau. Right, so this is about 2.2 times tau. So this rise time gives me sort of, you can see like it's the measure of the maximum bit rate I can operate at, right? So I can't turn off the device before this rise time because then my voltage hasn't reached its close to its steady state. Okay, so it gives you sort of some metric of what is the limitation of the bit rate from the photodetector response time. So again, so this time constant tau here, of course, we already talked about. So you can think of it as an RC time constant, right? So where R typically is given by the load resistance you put, the internal resistance of the photodetector is typically quite small. Okay, so the load resistance typically used are 50 ohm is sort of the standard smallest one, but you can use higher values. And in some places you will see load resistance used in kilo ohms, 10 kilo ohms, something like that also. Okay, and then the capacitance, as I said, is basically the capacitance of the device. Okay, so you can again, if you just think of this as some parallel plate capacitor here, right? So it's like a dielectric of width, something proportional to W, right? And you know, like the capacitance for a parallel plate capacitor goes inversely with the distance between the plates. So this capacitance here is basically the device capacitance from the PN junction. So this also known as junction capacitance. So that's just this epsilon is the permittivity of the material here. So you know that epsilon is basically epsilon naught times square of the refractive index, right? So n is 3.4. So right, so the permittivity is about 10 times roughly the free space permittivity. And then you have a cross-sectional area divided by the width. So width we can roughly assume to be, if we say that the depletion region width is almost the full device width, then we can roughly replace this distance between the plates as sort of roughly W. Okay, and A is sort of so that depends on the dimensions of the device. So what is the thickness into the board, and then this length here, product of that. Okay, so that's sort of the time constant coming from this RC kind of circuit that is made. Okay, but there's also another contribution, which is from the transit time of the carriers. Okay, so this is what we had talked about, right? So you generate some carriers here, and the time it takes for them to come to the electrodes, right? So you can roughly think of it. So what is that's sort of like the average velocity of the so the width of the device divided by the average velocity of the carriers, right? So this is something like W divided by some velocity of the carriers. Okay, and again we said that velocity is very small in the diffusion region and fast in the drift region. So if again you can make the depletion region width almost the whole device width, then this V average here will basically just be the drift velocity, which is very high, like 10 to the 5 or 10 to the 6 meters per second. Otherwise, it will be some combination of the drift velocity and diffusion velocity, and the diffusion velocity is really slow. Okay, like 10 to the 2 or 10 to the 3 meters per second. So 2-3 orders of magnitude slow, smaller than the drift. Okay, so you can see that these two have sort of opposite scaling, right? So if I want a fast transit time, I want a small w, right? I want the carriers to quickly go across my device. But if I have a small w, that increases the capacitance of my device and increases the RC time constant. Okay, so we have these two sort of opposing time scales or effects. So again, so you can't make W too small or you can't make W too large. So again, so one rule of thumb which is used, like we said, is sort of you make it 3 times this penetration depth, and where so now basically you have sort of equal contributions from the RC and the transit time. Okay, so as I said, so typically this W is between, let's say, 3 to 10 microns for typical in-gas detectors that are used. Right, so equivalently, I can think of if in the frequency domain, like the detector. So if I take the Fourier transform of this exponential function, you know, I get like a low-pass filter kind of response in frequency. Right, so if I look at the photodetector frequency response, it looks like a low-pass filter. Again, if I look at the bandwidth here, so delta F looks like 1 over 2 pi tau. Okay, so this relationship we also had for the sources, right? So the modulation bandwidth is inversely proportional to the time constant. So now again, so let's say we are operating at bit rates of a few gigabit per second, or even tens of gigabit per second, right? Which is sort of what we do for modern telecom systems. So this delta F has to be larger than the bandwidth of the signal that you're trying to detect, right? So you can see what timescales you need here. So for example, if you need like so typically this delta F is kept somewhere around the bit rate. Okay. So you can tailor this bandwidth. So we'll see, we can also have some additional circuitry around the detector to modify the effective bandwidth also. But anyway, so it's an interplay between detecting your signal and also limiting the amount of noise that you introduce, right? So if you have a large detector bandwidth, then of course you can detect faster signals, but also you introduce more noise as well. On the other hand, if you try to make the frequency or the frequency bandwidth is too small, then the noise is low, but now you start distorting the signal because you're not fast enough to detect the whole signal. So let's say if you want, for example, a gigahertz bandwidth, then basically you need about 100 picosecond response time from this relation. So if you want to go to 10 gigahertz, then you need to go down to 10 picosecond response. Okay. And people have demonstrated detectors even up to, let's say, 100 gigahertz bandwidth with these in-gas detectors. So just a word on this. So if you look at the time constant from the transit time, right, we can write it as a drift plus diffusion, right? So again, if so, this is W over VD. Okay, and this VD is about typically like 10 to the 5 to 10 to the 6 meter per second. Again, if W is a few microns, then you can see that this drift will be sort of 100 picoseconds or less. Okay. Whereas diffusion, so W by, okay, so maybe I should write dr and then we drift here. Okay, so this drift is like 10 to the 3 to 10 to the 4 meter per second or something. So this tau drift comes out to be like a few nanoseconds, right? Like let's say 10 nanoseconds for a few micron distance. So you can see that this drift loss diffusion is really a killer, right? You can't get anywhere near these time scales if you have an appreciable diffusion component in your device. Okay, so typically what is done is this region is made almost to the width of the device. We'll see how that's done to eliminate this diffusion component. Okay, so the specific modification that is done to have only drift contributing to your detection is to introduce an intrinsic region between the P and N regions. Okay, so that's why you might see in many places they're called pin photodiodes. So P, then intrinsic region, and then N. Okay, so basically now the device looks like this. You have a P, you have an N, and then you have a long intrinsic region in between. So undoped region in between. And now let's say you have light incident. And again you have reverse bias here, some load resistance here. Photocurrent generated. Okay, so here basically, if you look at the electric field, that electric field was high in this depletion region in between, and then sort of very low or non-existent outside the depletion region. So the velocity was high only in the middle of the depletion region. If I look at the electric field for this kind of device, so now, of course, there is some depletion region here into the P region and N region, but it extends all over the intrinsic region. Okay. So if I look at the electric field, it looks something like that. Okay, so there is a high electric field maintained throughout the intrinsic region. Right, so basically what you've done is like put an intrinsic region, and then if you extend the intrinsic region, this electric field just gets extended across the intrinsic region. Right, and now if your intrinsic region is much longer than the P and N regions, then over almost the entire device you have this high electric field, which makes a carrier move very fast across the entire length. Okay, and then you can do a further modification just like for the sources, right? Remember we had this double heterojunction kind of structure so that the light emission only happened in this. So we had an active layer there, right, between the P and N regions. And the active layer band gap was smaller than the P and N region, so that the carrier sort of collected in the active region and recombined only there. So we can do something similar here. So we can have the band gap of the intrinsic region smaller compared to the P and N region. So such that the light incident here, the band gap for the P region is larger than the wavelength or the energy corresponding to the photon. So it doesn't get absorbed in the P. The intrinsic region has a lower band gap, so the light absorption happens in the intrinsic region and again not in the N region. Okay, so if you do that double heterojunction kind of design, then you also ensure that basically the absorption and the carrier generation is happening only in the intrinsic region, where the electric field is higher. Right, so then basically your optical power goes something like that. So this is your incident power, right? And then you start absorbing once you get to the intrinsic region, and then you have this. Okay, so the effective absorption width is basically the width of the intrinsic region, which has high electric field, right? So basically, all your carriers which are generated due to absorption of photons are all moving with a drift velocity. So you sort of eliminate the diffusion component altogether, right? So if I draw an energy level diagram like this, so okay, so this is the P region, N region. So the photon energy is something like that. So here it's smaller than the band gap of the P and N regions, but it gets absorbed in the intrinsic. Okay, so once you have these photocarriers here, they quickly move to the contacts. Okay, so for example, you can have the P and N regions again, like indium phosphide, and this one like InGaAs. Right, so if you maintain this ratio of the mole fraction of the indium and gallium versus arsenic gas phosphide at this 0.45, then you know that these are lattice matched. Okay, so for these spin photodiodes, for example, typically if you have a width of the intrinsic region of about 4 microns, then like you can easily get the bandwidth to be 10 gigahertz. Now you only have drift. Okay. You can try to play some more tricks like to enhance the light absorption, so make this even smaller, but still maintain the quantum efficiency by having like some cavity kind of structure here so that the light bounces around a few times. And so people have, as I said, demonstrated photodetectors working up to, let's say, 100 gigahertz. Okay, with efficiency, let's say, fund efficiency is between 50% to 80%. Okay, and so typically, so we see here the typical width of the device is few microns. The reverse bias voltage applied is typically, let's say, around 5 volts or so. Right, load resistance used here is, let's say, between 50 ohms all the way up to maybe 10 kilo ohms or sometimes even higher. Okay, so that's the primarily this is the most popular kind of photodetector which is used, the pin photodiode, right, which gives you responsibility about, as I said, it can give you up to close to 1 amp per watt at the telecom wavelengths, and with bandwidths of a few gigahertz, up to 10 gigahertz, let's say. Right, so we saw that, for example, you can detect if your detected power is, let's say, above tens of microwatts, 100 microwatts or close to milliwatt or so, then you're much above the noise floor and you can easily use pin photodiodes. But let's say if you want to detect much weaker signals, so much lower incident power here, let's say now close to microwatts or maybe even into hundreds of nanowatts or below, then basically pin photodiodes just don't have enough, the responsibility is not high enough, right? So that your signal is buried in the noise. So there is another type of photodetector that you can use to enhance the signal even further, or in effect to obtain a larger responsivity. And that device is known as an avalanche photodiode, which also you might have heard about or studied a little bit already. So it's a little bit more complicated device than the twin photodiode, and also consequently more expensive. But it gives you maybe a 2 orders of magnitude enhancement in the responsivity, effective responsivity. We'll see how. Okay, so as the name suggests, there is an avalanche here, right? So you create some kind of avalanche process. So like for example, in the high mountains, you get these avalanches, which is basically you start with a small snowball, and then as it rolls down, it keeps picking up more and more snow, and eventually it becomes such a big giant mass that sort of like the whole snow of the whole mountain is collectively down. So a similar effect one can use here to enhance the photocurrent. Okay, so you generate these carriers, but somehow if you can make the carriers which are generated to create even more carriers, okay, something like stimulated emission for the sources, right? If you can do something like that, so we generate some carriers, but those carriers now somehow generate more carriers on their own, then that will sort of enhance the efficiency of our device. So what is done is that we put what is known as an avalanche layer. So you have the usual, so let's say this is the intrinsic region, E, N. Okay, so we start from the same kind of structure here, but the change that you do is, first of all, you increase the doping in the P and N regions quite a bit, let's say by an order of magnitude or 2. So these are now P plus and N plus. And then you add another thin layer of P just before the N. Okay. And similar now, so you apply sort of reverse bias to this outer P-N junction. Okay, so but now what has happened is, so if you look at the electric field, right? So in this case, we have sort of a constant high electric field across the intrinsic region. But now, because of this additional P region here next to the N, this creates its own depletion region, right? This Pn, which adds on to the depletion region of this outer Pn junction. Okay. So just here, in the second p-n junction, the electric field is enhanced even further. So okay, so that's how the electric field looks like. Okay, so in addition to this constant sort of high electric field across the intrinsic region right here, now you boost the electric field even further in the small region here. Okay, and now if you design such that this electric field exceeds what is known as the breakdown field. Okay, so there is some level which is known as the breakdown field. So if the electric field in the material exceeds that value, then what you start getting is this avalanche multiplication. Okay, it's this sort of, you cross this threshold of so this analogy of this snowball now just picking up more and more snow as it rolls down to become a giant mass. So basically, the electrons and holes which are in this region where the electric field is higher than the breakdown region, basically what you start getting is impact ionization. Okay, so basically electrons and holes creating more electrons and holes. Through what is known as impact ionization. So basically, as the name suggests, the process is something like you have an electron flowing, right? It hits another atom, and that energy of collision ionizes that atom, right? So this fast-moving electron sort of is incident on a neutral atom, and then it excites the electron to the conduction band from that atom. Okay? So basically, an electron incident on a neutral atom, and then creating also this electron going into the conduction band. So now you have the original electron, and now this extra electron also in the conduction band, and also an hole in the valence band because of this electron being excited into it. Okay, so basically, an incident electron has now created an extra electron hole pair after this impact ionization process. Okay, so all the carriers passing through this region where the electric field is greater than the breakdown field end up doing this, right? So you can see that the number of carriers gets multiplied by this avalanche process, basically enhancing the photocurrent that you get. Okay, so basically you can think of this intrinsic region whose width is, let's say, W. This is the absorption region, where the light is absorbed and carriers are first generated. And then this thin region here, let's say of thickness D. So that's the gain or avalanche region. Okay, so this region here is operating like a pin photodiode. Okay, so you can imagine like the primary photocurrent you generate here is something like responsivity times the incident power. Okay, and then in this region here, basically you have gain so that you multiply the photocurrent. So let's say this is some internal, then external. You multiply by a gain factor or a multiplication factor, which is much bigger than 1. So your effective photocurrent coming out, or the effective responsivity, will be much larger than the gain photocurrent. Okay, so one can model this avalanche multiplication region in a simple manner to sort of estimate how much gain or multiplication you get depending on the impact ionization parameters for a given material, right? And consequently, what should be our thickness of this avalanche region here, or which is roughly the thickness of this P region that we've introduced. Okay, so imagine, so now let's say, so look at this region of thickness D, the avalanche region. So let's call this x equal to 0, x equal to D. Okay. So let's say some electrons are entering from this side, right? And here now you're generating more and more electrons. So now here you have many more electrons, right? So if the electrons are flowing like this, you know that the electron current is like that. I have sort of shown an arrow with increasing thickness to show that the current is increasing because of this impact ionization process going on here. You have holes going the other way. So again, holes going like that and then creating more holes here so that now you have many more holes on the other side. And you can see that the hole current is also like that in the same direction as the electron current. Right? Maybe I should. So this thickness is the other way around, right? So there are more electrons here, so the current is higher here. Whereas for holes, the current is higher here, right? Right? I hope that picture is clear. Okay, so if I write, for example, how the electron current varies in this region, so the current is a function of position x within this multiplication region. Okay, so that I can write as a combination of two things. One is, so as I said, so you could have an electron causing ionization of an atom. So an electron creating an electron and hole pair. That is denoted by this first term, right? So you have some electron current or some electrons incident, which creates more electron, right? So di by dx is proportional to I, or die by dx is proportional to IE. So that's electrons causing more electrons. With this proportionality factor here, alpha sub E is basically the electron impact ionization coefficient. Okay, and then the second contribution is basically now, let's say you have a hole now causing, having a collision with an atom and then causing ionization. So that now is proportional to the hole current, and this is now the whole impact ionization coefficient. Right, so this alpha E, alpha H are material constants. Right? Similarly, I can write for the hole current. Also the same two contributions. Okay, except there's a minus sign here because the holes are flowing in the opposite direction, right? So when I generate more holes, they have a current opposite to the electrons. Or the holes are flowing opposite to the electrons. So if this gives you sort of the number of holes being generated, like this number here is giving me the number of electrons generated, and the same thing is giving me the number of holes generated, but now they're moving in the opposite direction. Okay, so of course these are also functions of x here. So if I define the total current as the sum of the electron and hole current, okay, you can see that. So just from these two equations, if I add them, then the total current is an invariant. Okay, under this sort of model, right? So uh, in other words, so if I look at this multiplication region, so as these arrows suggest, so the electron current is going up from this side to this side, but the whole current is going down from this side to this side. Okay, so this is the electron current, this is the whole current, and if you add both of them, then you're getting something which is independent of the position. Okay, so one thing to notice, so basically you're generating carriers here, right? So the absorption is happening here. So you create an electron hole pair here. Primarily what happens is that the holes, because of this electric field, go this side, right? And the electrons go this side. Again, the speed is pointing from this to this, right? So the holes move along the field. So they go actually towards this P plus side. And basically it's only primarily, you can see the electrons which are going to this multiplication region. Right? Or in other words, if you look at the whole current, this actually should be like 0 here. Right? So x equal to d, from here there are no holes coming in. And from this side, it's basically the electrons which come here. That's the IE which is coming in at x equal to 0 and then gets amplified. Right? And this impact ionization is also somehow creating more holes here. Because the ionization process, every time you create an electron, you also create it. Right? So this is a current coming from the intrinsic region. So yeah, so with this total current being constant here, right? So and we see basically mostly what is happening is the electrons which are driving this process, right? So basically we can write the electron current or the whole current as the total current minus the electron current. Okay, and then substitute this into here. So then we'll have an equation just in the electron current. Okay, so now we have this equation for the electron current, which and IE is the only non-constant thing here, and this is an easy integration to do, right? So we just bring this to this side. This term is a constant. And now the electron current starts from some IE0, which is this level here. Right? So this is IE0 at x equal to 0, going up to now IE at D, the end of the avalanche region. And now at the end of the avalanche region here, basically IE at D is just equal to the total current, right? Because we're saying there is no whole current here, right? We are saying there is no holes coming here from the N plus side, there are no holes coming. So the total electron current here at the end of the multiplication region is just the total current. So this IED is just equal to I. Okay. So, or in other words, here IH at x equal to D, we are saying is 0. Okay, so yeah, so you can see, so this integration gives me a log, right? So it's easy to do. And then you just do some simple algebraic manipulations to get this multiplication factor, which is the total current out by the incident current, which is IE0, right? This is the incident current into the gain or multiplication region, and then it gets amplified by this much, right? So this is output by input, gives me the gain or the multiplication factor. So that comes out to be okay. So of course there is some factor of e to the something because here we get a log, right? And we have introduced another. So alpha e we already know here. D is the thickness of the multiplication region, right? And so Ka is the ratio of the hole to the electron impact ionization coefficients. Okay, so this is basically, so what we are saying is that the responsivity of the APD is basically m times the responsivity for a pin photodiode of similar construction or all the other factors being the same. If I just introduce this extra multiplication layer, that gives me an enhancement of this m times from the pin. Okay, so let's see what the values of this m can be for this for some typical parameters. So of course it depends on this Ka value, which is the ratio of the hole and electron impact ionization factor. So if you have a material where the electron impact ionization coefficient is much larger than the hole, which means only electrons are mostly causing this avalanche multiplication, and the holes are just passing through; they're not doing anything, right? So this is basically Ka close to or very small number, right? Alpha is much less than alpha e. So in that limit, you can see that m just now exponentially depends on the this thickness of the multiplication region, and of course only the electron impact ionization factor comes in here. Okay. And so typically for most semiconductor materials, alpha E is bigger than alpha H. How much bigger depends on the exact material, but typically alpha is always bigger than alpha H, which means Ka is always less than 1. Okay. If you look at the other limit, of alpha E and alpha H being this sort of similar values or close to each other, then if you take the limit of this expression for K equal to 1, you can see that M comes out to be this. Okay, so now there's almost like an inverse dependence on the thickness. And M can actually shoot up to a very large value for a thickness equal to 1 over this electron impact angle or a hole impact ionization coefficient, because both of them are the same. Okay, so this seems like very nice. I can get like really large enhancement in the current or the responsivity, but typically this is avoided actually because this also shoots up the noise, right? So you can imagine that if like infinite amount of multiplication is happening here, then any small thermally generated carriers which are not photo generated but just some background noise, dark current, or some thermally generated photocurrents, they will also get multiplied so much that you'll get a huge huge current without any even light inside. Right? So the noise will also be extremely large. So typically this scenario is sort of avoided anyway, and as I said, for most semiconductors anyway, alpha is at least bigger than alpha H. Okay. So you're away from K equal to 1. Okay, so let's see what some typical values are. So this is the impact ionization coefficient. So the alpha E or alpha H. You can see units is per length, of course. Just like an absorption coefficient. So this impact ionization coefficient is a function of the electric field, right? So remember, we had some electric field here, which was fairly high, but below the breakdown voltage. And then in this region, it went up above the breakdown voltage, which caused this breakdown. So basically, this ionization coefficient is a function of the electric field. So if I plot the electric field on the x-axis and then see how the impact ionization coefficient varies. So this is in 10 to the 5 volt per centimeter. Okay, so you can see we're talking about large values here. But again, remember that these thicknesses we are talking about are microns, and we are applying few volts. So we can easily reach these values. Just because the devices are so small. Okay, so if I look at silicon, we put some numbers here. So the x-axis is, let's say, log scale, it's not linear. Similarly, y-axis is log scale. So okay, so this is what it looks like for silicon. The solid line is the electron, and the dashed line is the hole. So you can see alpha is greater than alpha H for any particular electric field, and in general, the values go up with higher electric field. So you get more avalanche multiplication as the electric field increases. So this is silicon, which, as I said, we use for visible wavelengths. But if you go to in-gas devices for telecom wavelengths, then the values are even higher actually. Okay, so this electric field you can think of as almost sort of like the reverse bias voltage that we apply divided by the thickness of this multiplication region, right? Because almost all the voltage is dropped across this small region here, right? The field is very high here and then sort of lower everywhere else. So roughly you can estimate it as the reverse bias voltage applied divided by the thickness of this. Okay, so again, so if you apply something like greater than 10, maybe up to 100 volts. So for the pin photodiode, remember we were operating, let's say, around 5 volts. Here we go slightly higher, maybe 10 volts or 20, 30 volts. Some devices maybe even up to 100 volts. And this D, you can see if it's in the 1 to 10 micron range, right? Then we can easily reach these values of beyond 10 to the 5 volt per centimeter. So typically, like for example, you can have a 1 micron thickness here. The intrinsic region is, let's say, a few microns, let's say 4 or 5 microns, then 1 micron multiplication region, and then you can work with reverse bias voltage of 10, 20 volts. Okay, so the alpha E bar, so if you look at Ka for these in-gas devices, that's typically about 0.5 to 0.7. Okay, so alpha is bigger than alpha X, but maybe by a factor of 2, not by a whole big. So for such things, of course, you have to use the entire expression. You can't use either limit here. Okay, so that's great. Of course, we get a huge multiplication here, right? And so typical from here, for these typical values, the multiplication factor one can get is like maybe from 10, let's say, to all the way up to 40 maybe. Okay, so the current that you get out of APDs is at least an order of magnitude, maybe almost up to 2 orders of magnitude larger than what you get out of the pin photodiode. So now, of course, it doesn't come for free, right? So what is happening is that in addition to the carriers now flowing across the intrinsic region, now they're causing this multiplication, right? So there's an effective increase in the transit time across the this avalanche multiplication region, right? So you can imagine that they will move slightly slower through here because they're not just flowing; they're also causing this. They're undergoing collisions and causing this impact ionization. Okay, so there's an increase in transit time, which also just depends on this. So higher your multiplication factor, the higher or the slower the carriers flow through this gain region. So if you look at the frequency, so basically what happens is that the effective so if you look at an AC signal, right? So this M that we derived was sort of like the DC value, right? We're talking about a constant electron and hole current. But let's say now you have an AC signal, like so for example, your incident power is modulated at a particular frequency, right? So your carriers are being generated here are also varying with time. Because of this finite time that these collisions take and the ionization causing an increased transit time of the carriers, right? As you increase the frequency, this multiplication doesn't happen as fast, right? So basically, you can think of this multiplication factor being also a function of frequency, right? So if I change my incident light at a particular rate, the multiplication doesn't always follow that rate, right? So this goes down something like, so this M naught, which is what we calculated from that expression. But as you increase the frequency, okay, it goes down by something like, which again looks like a Lorentzian function with frequency, 1 plus omega square. Okay. And so now we have like tau E times M naught. So this is tau E is the what is known as the effective transit time, which is basically, so this tau E is roughly this factor Ka, right, which is the alpha H by alpha E times the actual transit time that we would compute from this width of the device divided by the drift velocity. Okay, and then you can see that is multiplied by this m naught. Okay, so this whole thing is like the effective transit time. So you can see that basically I'm increasing the transit time by a factor of m naught times Ka. Right, so if Ka is again like around 0.5, 0.7 and m naught is like 10 to 40, you can see that this effective or this tau E times m naught is about an order of magnitude larger than tau transit. Right, so if tau transit, let's ignore the RC time constant for a minute. If the transit time is the limiting factor which determines the bandwidth of the pin photodiode, you can see that for the APD that's much worse, right? Because of this enhancement in the or the slowdown in the transit time because of the multiplication. Okay, so again I can look at, so if you plot this multiplication of the gain as a function of frequency, it has again a low pass filter kind of response. And again, if you find like a bandwidth, it's like this, right? So it's the transit time, but now multiplied by this factor of Ka times the DC gain. Okay, so again, so let's say if this was 10 picosecond to something for just the pin photodiode, now like you enhance it by a factor of let's say 10 or something for the APD. Okay, so the bandwidth goes down. So this is something from here you can see that there is something like a gain bandwidth product, right? So if I look at the DC gain m naught times the bandwidth delta f, that is like a constant, right? It depends only on the device or material parameters. So this is like the usual gain bandwidth product or trade-off that you have for typically any kind of electronic device or anything in general actually, right? So you have this trade-off. If you want to increase gain, you have to reduce the bandwidth. Okay. So yeah. So typically the APDs that one uses for telecom applications, this m times typically can exceed 100 gigahertz. Right, so which means you can have, for example, a DC gain of 10 and a bandwidth of 10 gigahertz, or equivalently like a bandwidth of 100 gigahertz without any DC gain. Okay, so we've exceeded time already, so we'll stop here. Any questions? So today basically we discussed sort of the basic construction and the characteristics like responsivity and bandwidth for the two main types of detectors used, pin photodiodes and avalanche photodiodes. 。  . 。  . 。 . . . . . . . . . . . . . 。 . 。 . . 。 . . . . . . 。 . . 。 . . . . . 。 . . . . . . 。 . . . . . . . 。
Avalanche photodiodes.
So typically, if you want to go to higher speeds, then you go for pin detectors. If your primary concern is low light levels and not so much the speed, then you go for APDs. Right? And APDs you can also with some additional modification and tricks, you can make them even more sensitive. And as you know, some of you might know that you can also get APDs which are sensitive down to the single photon level. Okay. So those are known as single photon avalanche photodiodes, or SPADs, where basically like one incident photon can give you a current pulse. But so usually that kind of thing is not utilized in optical communications. But just so you know, those also exist.